Perfect, perfect. Cool. So we have our carbonyl nucleophile. We just talked about hydride nucleophiles. Let's move on to oxygen nucleophile. So in the case of an oxygen nucleophile, I'm going to, instead of having hydride attack, I'm going to need a nucleophile that contains oxygen. Most of our nucleophiles that contain oxygen will be alcohols. So here on the left-hand side, I have a carbonyl group, and here on the right side, I have ROH. ROH can represent any alcohol. So R can be any alkyl group. If this was CH3, this would be methanol. This was CH2, CH3, it'd be ethanol, whatever alcohol group you have. So we know that alcohols in this form are not good nucleophiles. We've learned that in the past because oxygen atoms are small and there is no formal charge. So that makes them not very polarizable, not very good nucleophiles. Either way, we know that this is a very great, very excellent electrophile. So our nucleophile hypothetically can attack anyways, even though it's weak. So that's what I'm showing with this curved arrow, that the electrons are going to attack our carbonyl group, our positive center, our electrophile. So when we draw arrows, we recall from OChem 1 and also from OChem 2 that we draw the arrows starting at the electrons and then the head points to the electrophile. So let's keep going. That'll push up the electrons from the double bond onto the oxygen, and we'll get this product. We'll get our alkoxide ion on the left, and then we'll get this group on the right. But let me tell you something, students. I mentioned that this alkoxide ion is very unstable. I also mentioned that carbonyl groups will try to reform if they can. And the only way they can reform is if we expel a group. We noted that we can't expel hydrogen or carbon. But if I bring these electrons back in, I can't expel this carbon and I can't expel this carbon. But you know what I can expel? Is this oxygen, because it's not carbon or hydrogen. I can expel this oxygen with its electrons because it's not a hydride or a carbide. So what'll happen is that's exactly what'll happen. We'll get our electrons to come back and then this will leave. But then students, I just start with I finish what I started with. I finished what I started with, which is a carbonyl group and my alcohol. So we saw that that is not a good synthesis strategy. So what if, to keep our carbonyl group from reforming, we just use a nucleophile that is more nucleophilic? Instead of using an alcohol, what if I just use a stronger nucleophile? Let's try that, students. So now, can you all recognize what kind of substrate this is that's going to attack? Is this still an alcohol? Y'all are saying, Selena saying that this is an alkoxide. And yes, Selena is right. So this is an alkoxide ion. So an alkoxide is simply a deprotonated alcohol, and it's a way stronger nucleophile because now we have a negative charge on the oxygen. So a charge will make a nucleophile stronger. So it'll attack in the same way our carbonyl group, and that'll push up the electrons onto the oxygen. And we'll get this product instead. We get in, hopefully you can recognize this is an ether now, and this is our alkoxide ion. Once again, though, will our carbonyl try to reform? Yes. Can it reform? Yes, because this is not hydride or carbide. So what will happen is the electrons will come back, and then our ether group will be expelled again to form an alkoxide. So making the nucleophile a stronger nucleophile will not work. You'll still get a carbonyl group to reform. I hope that I'm making sense to you all. What I'm trying to show you all is how we can add oxygen. We cannot add oxygen using just any nucleophile because what will happen is the carbonyl will reform. So we can't use an alcohol and we use an alkoxide. Instead, I'm going to show you a different strategy. that will cause our carbonyl to not form again. So once again, if we make the nucleophile more nucleophilic, it won't work. Instead, we have to make our electrophile more electrophilic. So instead of changing my nucleophile, what I need to do is change my electrophile. I need to make that carbonyl group more electrophilic. I need to make it more positive so that carbonyl does not form again. So this was our starting carbonyl. We noticed that it's a very positive center. It's polar because of electronegativity difference. Something I can do, students, is I can make this bond even more polar. I can make this positive center even more positive. I can make this electrophile more electrophilic. And the way I do that is by using an acid. Students, what do acids do? They donate protons. Exactly. Of all the substrate, of all the atoms here, we have carbon, oxygen, and then some alkyl groups. Which do you think will accept that proton from this acid that I'm symbolizing as HA? The carbon atom? The oxygen atom? What will do it? Oxygen, says Andrea. Andrea's correct. Jackie also says oxygen. Very good, Andrea and Jackie. The oxygen, being, having its lone pairs, will, via an acid-base proton transfer, be a base that accepts the proton from our acid. So we're going to get this. So we protonated our carbonyl. Protonated our carbonyl. This was protonation. Students, I'm going to be using that word a lot. Protonation. Protonate. To protonate means I add hydrogen as a proton to my substrate. Protonate. There's another term I'm going to be throwing out in the next couple of slides. Deprotonate. Deprotonate means I remove hydrogen from my substrate. Remove hydrogen from my substrate. So protonate is I add hydrogen as a proton. Deprotonate means I take away hydrogen as a proton. So in this case, we protonated our carbonyl group. We protonated our oxygen. But look what that created. A positive formal charge on the oxygen. Let me tell you all something. Oxygen hates being positive. It hates supporting a positive formal charge. It hates doing that. It's not, oxyanions are very unstable. So what will happen is the same thing that was happening before. The electrons being shared in the double bond are going to move more towards oxygen because it's more electronegative. But now that it's not only electronegative, now that it also has a positive moment, a positive formal charge, it's going to push these electrons even more toward itself, making the carbon atom even more electrophilic. Therefore, students, we saw by protonating our carbonyl group, I made my whole structure more electrophilic because the oxygen, now having a formal charge, now being a positive oxygen, will pull the electrons even more harshly toward itself in order to eliminate that formal charge, making our carbon atom way more electropositive, making this center way more electrophilic, way more positive. So this is a protonated carbonyl group. When we do this, students, we can also call this product activated carbonyl group. So if I say protonated, that means I added H+, but I can also say activated, and that means I also added H+. So I activated it, I gave it a charge, and now it's going to it's going to want to get rid of that charge because it's activated. It wants to be deactivated. So the protonation of a carbonyl group by an acid will activate it for a nucleophilic attack. Let's keep going. We have our activated carbonyl group on the left, and now I have my alcohol on as a reagent. Now that my electrophile, the activated carbonyl, has become more electrophilic, because of protonation, I can attack now with my nucleophile. So the alcohol, using its lone pairs, will attack our electrophile, and that'll push up the electrons onto the oxygen. You see that? So now we have the electrons on the oxygen. It already had one lone pair, now it has two. And now we got our alcohol moiety to attach. Will the carbonyl form again? No, because for the carbonyl to form again, we have to get these electrons to come back down here. And we saw that if we do that, we're going to get this activated carbonyl group. And it doesn't want to be activated. It's not stable. So it's going to stay like this. We're going to get this hydroxyl group to stay. We saw, students, in order for me to first have an oxygen nucleophile attack, I need to activate my carbonyl group. And I activate it via an acid-base proton transfer that protonates my carbonyl group and allows it to become more electrophilic so the carbonyl group does not reform again when the nucleophile, our alcohol, attacks. I'm going to throw out another terminology to you. I want you all to know what kind of product this is. This kind of product has a special name. It's known as a hemiacetal. Hemiacetal. Hemi, the prefix hemi, you might know, means half. So this is half of an acetal. Right now I'll show you what a full acetal looks like. But for now, this is a hemiacetal. A hemiacetal is a derivative of an aldehyde or ketone in which our carbonyl atom, instead of now having a carbon-oxygen double bond, we replace the double bond with a single bond to a hydroxyl group and a single bond to an alkoxy group, an ether. So that's what a hemiacetal is. Hydroxyl and alkoxy group single bonded to that central carbon that used to be part of a carbonyl group, a hemiacetal. So that was the first step, students. But we're not going to finish with our hemiacetal. We're going to keep going, and we're going to make this hemiacetal into an acetal. So how do we do that? We have to keep protonating and deprotonating. So through protonation and deprotonation, we can get that hydroxide group to exit the hemiacetal, and we can instead form two ethers. So I'll show you. What I want to do is I want this hydroxyl group to leave because I want to have two alkoxy groups. Two alkoxy groups. I don't want to have a diol. If I wanted to have a diol, I would have instead used water. But in this case, I used alcohol because I'm trying to add ether groups. So I'm going to do that now. Here on the left-hand side, I have my hemiacetal. What's going to happen is I am now going to have a base in solution. The base is that same acid that we used at the beginning. The same acid that activated our carbonyl group now is a conjugate base, A-. That A- will accept a proton, but not from a hydroxyl. It'll instead accept it from the ether group, this alkoxy group, because it has that positive formal charge on the oxygen. So to get rid of it, we'll have acid-base proton transfer, and that'll move back the lone pairs onto the oxygen, and now I have my stable hemiacetal group, deactivated hemiacetal group. Once I have my deactivated, deprotonated hemiacetal group, I can continue the reaction. But notice, students, that I first have to deprotonate it. So remember, I'm going to keep throwing out those terms to you. Protonation, deprotonation. So far, we've had one protonation and one deprotonation. So now we have a deactivated hemiacetal. So let's keep going. Now I have my deprotonated hemiacetal. It's neutral, but I don't want to have hydroxyl group. I want to have two ether groups. That'll make it an acetal. So what I'll do, students, is via another acid-base proton transfer, I'm going to activate the hydroxyl group. When I activate the hydroxyl group, students, I get this product. Can anyone tell me what group this is called? It's no longer hydroxyl. This is now a different group. Roxana says water. Anyone agree with her, or is it a different group? If you agree with her that this is water, type in water. No one agrees with her? Oh, Lesbia agrees with her, and so does Uriel and Casey and Skyla, and they're all correct. Yes, this is water. Students, I need you to go back into the inner recesses of your subconscious, and I need you to recall to me some special property about water when it's attached to our substrate. What is water that a hydroxyl group is not? OMG, yay. You all said the answer. I'm so proud of you. Yes, it's an excellent leaving group. It'll leave the substrate. Why? Because it's the... What are good leaving groups? As opposed to bad leaving groups? What makes a good leaving group into a good leaving group? They are conjugate, Jackie said it, conjugate bases of strong acids. So water is the conjugate base of the strong acid hydronium. So it'll exit the substrate. It's a good leaving group. Perfect. Y'all made me so proud. So here we saw a protonation. We protonated our hydroxyl group, made it into water. And water is an excellent leaving group because it's the conjugate base of a strong acid hydronium. So that's exactly what's going to happen now. After we protonate our hydroxyl group to make water, water will exit the substrate, which I'm demonstrating with these arrows. It'll take its electrons with it, and then the electrons from the ether will move down to form a double bond and replace that single bond that left. So now we have this structure. Similar to a carbonyl group, except now we have that R group from the alcohol, or from the ether in this case, also attached, but it's activated. And then we saw that water exited the substrate. So now we formed once again our carbonyl group, but it's still activated since it has that R attached. Activated carbonyl group. So now what I'm going to do, students, in order to deactivate that carbonyl group is I'm going to attack it with a nucleophile. We learned that when a carbonyl group is activated, it's a very good electrophile, so it can be attacked by a nucleophile. So now I'm going to have one more mole of that same alcohol attack nucleophilically our carbonyl group, and I'm going to have the electrons pushed up onto the oxygen, and I'm going to form this product, ether and activated ether. Ether, activated ether. This was a nucleophilic attack. Lastly, to get rid of that formal charge, what should I do, students? On the oxygen? How can I get rid of this formal charge that I don't want? Deprotonate, says Skyla. Perfect. She used the exact word I wanted her to use. Deprotonated. So a base in solution, another conjugate base, will deprotonate our activated ether group, and that'll form two ether groups, a diether, ROOR. This is what we call deprotonation, and this is our acetal. So another term I threw out there, hemiacetal was hydroxyl group, ether group. Hydroxyl group, alkoxide. Acetal is two alkoxides, two ether groups. Perfect. So an acetal is a derivative of an aldehyde or ketone with two alkoxy groups on the former carbonyl carbon atom. So now that is what our acetal is. That was a lot of steps, students, in order to get our original carbonyl group to form an acetal. So we're going to summarize, okay? Here I have a summary of all of the reactions. And I want you with me to summarize the steps. So let's go one by one. Here we see our carbonyl group becoming activated. And that happens when I expose it to an acid. So this is called what? When I'm donating hydrogen to my carbonyl group. Okay, so Uriel, Lesbia, Jackie, Skyla are saying protonation. Yes, protonation. First step. Protonation turns our carbonyl group into an activated carbonyl group, which is an excellent electrophile. And now we have our oxygen nucleophile, our alcohol that is ready to attack. So it'll attack nucleophilically, and we get this product. We get, what kind of product is this called? Where it's a hydroxyl group and an alkoxide group where our carbonyl used to be. We call that A. Jackie says hemiacetal. Skyla, Roxana say hemiacetal. Yes, hemiacetal. We noted that to deactivate our hemiacetal, because we have a positive formal charge on the oxygen, we need to have that conjugate base that we formed at the very beginning accept the proton from our substrate, remove the proton from our substrate. What is that called, students, when we remove the proton from the substrate? Skyla says deprotonation. Jackie, Uriel say deprotonation. Yes, deprotonation. Very good, students. Y'all are going to be so ready for biochemistry because you're going to hear those terms all the time in biochem. Okay, so we deprotonate it, but I don't want a hemiacetal. I just want an acetal. Now, students, if the final product is a hemiacetal, you can just stop there and you'll be fine. So if we're asking you to synthesize a hemiacetal, you can just do that and leave it there. In this case, we're showing you how to not only go to hemiacetal, also go to a full acetal. So the next step we're seeing is to remove our hydroxyl group. We need to protonate, right? So we're going to have a protonation, and we're going to form an activated hydroxyl group. This activated hydroxyl group is now water, and water is an excellent leaving group. Very good. So Sophia, Paulette, Casey, they're all saying leaving group. So we're going to have a loss of a leaving group that leads to this activated carbonyl group once more. That activated carbonyl group will be nucleophilically attacked once more by another mole of our alcohol, and then we'll get this activated ether. And to get that activation removed to form a neutral ether, we're going to do what? Deprotonation. Perfect. And that gives us our acetal, two alkoxy groups. So students, summarizing, it's two protonations, two deprotonations, two nucleophilic attacks, and one loss of a leaving group that give us our acetal. If we're trying, however, to just go to our hemiacetal, it's just these three steps: protonation, nucleophilic attack, deprotonation. So now let's look at this. Well, are there any questions, first of all, before we do our next problem? I hope this is making sense to you all. Then let's start. Let's give the IUPAC name for this substrate and then draw a mechanism for its formation, for its transformation. So we have our substrate on the left and we have our product on the right. Students, what kind of substrate is this? What kind of structure is this? I hope y'all, ketone, perfect. It's a ketone. It's an internal carbonyl group. It's a ketone. Can anyone offer the name? So remember, if we give the IUPAC name, you can call this, for instance, 1, 2, 3. This is dipropyl ketone. I'm not asking you the common name though. I'm asking you IUPAC name. So y'all are saying hepta 4,1. So let's see, 1, 2, 3, 4, 5, 6, 7. Very good. So it's hepta, and it's at carbon 1, 2, 3, 4. Perfect. Hepta 4 on. So I'm taking hepta 4 on, and I'm transforming it into another kind of structure. What kind of structure is this using the terminology I gave you earlier? Roxana and Skyla say acetal. Very good. It is acetal. So this is heptane 4 acetal, but you don't have to know the IUPAC name for this at all. But good that you recognize that. So let's see how we get there. I'm going to stop sharing the screen. And I want you all to take out your sheets of paper and be solving it with me. I want you to practice drawing these structures. So we have 4, 5, 6, our ketone. And we called this ketone heptane. Oh, it's not letting me type. There we go. Heptane 4 on. We're exposing it to a certain series of reagents that'll give us this product. So students, I didn't give you the reagents. That's because in a lot of reactions you're going to see, especially on the final, but maybe on this test, you might be asked to do what we call retrosynthetic analysis. I've mentioned this before, but retrosynthetic analysis is when you're given a final structure, such as this one, this acetal, and the original structure, and you have to come up with the steps yourselves and the reagents yourself that lead from the formation of the final product from the initial product. So that's called retrosynthetic analysis. Retro means looking back. So you look back and you think, what could have gotten me from step 1 to my final step? So students, we know this is a carbonyl group. We know it's a good electrophile. But what do we need to do first in order to make it an even more excellent electrophile? Protonate. Yes, we need to protonate this alcohol. Very good. So I'm going to erase this product that I drew because I don't want it there anymore. Or I don't want it yet. This takes forever. Let me just redraw. What acid should I use, students? If we're going to make, because that is the first step, protonation. Not a carboxylic acid. I'm going to use, so Skyla says sulfuric acid. You can use sulfuric acid to protonate, but even better, what'll usually happen is you'll have sulfuric acid. Oh, misspelled it. You'll have sulfuric acid and you'll have an alcohol. In this case, we're going to use CH3CH2OH, also known as ethanol. What'll happen is that the alcohol will protonate first, or sorry, all alcohol will be protonated by sulfuric acid in solution. So we're going to get CH3CH2OH2, or simply ETOH2. And that's going to be the source of our alcohol, our acid. Our alcohol is going to be the source of the acid. and you can use sulfuric acid to protonate it. But yes, that's just a technicality, but you can use sulfuric acid just by itself, or you can use the alcohol by itself. But first, let's just use a protonated alcohol, ethanol. So what we'll have is we'll have this form. Protonated carbonyl group. And that makes this into a very excellent electrophile. To get my final product, you saw, hopefully, that what I'm going to have to get is an acetal group that has, what's it called? Ethoxy. They were ethoxy alkoxides. So ethoxy alkoxides come from ethanol. So ethanol, with its lone pairs, will nucleophilically attack our activated carbonyl group, and we're going to get this product. And now there exists a positive formal charge on our alcohol. So we've done the first steps. We protonated, and then we had our nucleophilic attack. And I realized I forgot. There we go. Nucleophilic attack. Now, I should like to get rid of that positive formal charge that I have now placed on the alcohol. Here I have a hemi acetal that I just formed. So in order to remove the formal charge, I need to, and by the way, the formal charge is on the oxygen, not on the ethanol. I'll put it over here instead. What do we need to do to remove that positive formal charge from my alcohol? From here, my alcohol group. Deprotonate. Deprotonate. Deprotonate means remove. So we're going to deprotonate. Good job, Casey. So we're going to deprotonate. And what we're going to do is we're going to use another mole of ethanol to accomplish that. So our conjugate base from the very beginning can accept that proton. So it'll take the proton. And we'll get this product. It's probably drawn better like this. There we go. So now it's deprotonated, and I formed my deactivated hemiacetal. Students, did I want a hemiacetal as my final product? No. Sophia says no, and she's right. No, I didn't. I wanted two ethoxy groups, not just one ethoxy group and a hydroxyl group. So what I'm going to do is I'm going to have to get rid of this hydroxyl group. Who can remind me how we get rid of hydroxyl groups? Protonate, yes. And that turns our hydroxyl group into a water group, an excellent leaving group. So let me show how that happens. I'm going to erase the screen. And I'm going to start with the product we just synthesized, the hemiacetal. We have OH, and we have OET. Using another source of alcohol, I can still use that same ETOH2 that I just made by a deprotonation. I can use, sorry, an alkoxide ion. How do I move this? Yeah, here we go. So I can donate H+. Can donate one of these H's. to here. So by an acid-base proton transfer, I'm going to turn that hydroxyl group into water. And I'm showing the hydrogen that came from that activated ethanol molecule in solution. And then we also had our ether group, our ethoxy. Okay, and now we've learned, we've identified, we've recognized this entire semester, or for a lot of this semester, that water is an excellent leaving group because it's the conjugate base of the strong acid. So what it'll do is it'll exit the substrate with its electrons, and then 2 electrons from the ether will come down to another carbonyl group. So I'll get this. So notice that this is from here, and that this new bond came from 2 lone pairs, or a lone pair that exists on the oxygen atom. And that replaces the bond that was destroyed when water exited. Okay, and this is a protonated ether group. Protonated ether group, or a protonated carbonyl group, is a very good electrophile. So what's going to happen if we have a very good electrophile is we'll have another nucleophilic attack by another ethanol moiety. So ethanol, in the lone pairs that exist on the oxygen, they will nucleophilically attack our activated carbonyl group, our good electrophile. And what we'll get in the end is this product. We have OET, and we have another OET. To clarify, this second ETOH was from here, and it's actually ETOH. The whole thing attacked. The whole thing attacked. And because it attacked with hydrogen, this oxygen has a formal charge. A positive formal charge. I don't know if y'all can see what I put, the positive formal charge right there. How do we get rid of that positive formal charge? We do another. So this over here at the top was a protonation. And that last one, if we want to get rid of this formal charge and just get ETO, ethoxy, deprotonation. Deprotonation, perfect. So I'm going to need a deprotonation over here. And we know we can get that from another conjugate base in solution. So what I'm just going to do to simplify things is assume we already had our deprotonation and just get rid of that hydrogen and that formal charge. So is this not my final product? Is it? What kind of product is this? Acetal. Perfect. Acetal. So there y'all saw how we form an acetal. I hope that made sense. I hope y'all were following along with your pens and papers, drawing out these mechanisms because they're going to become so important. Now it's 8 p.m. That means my review session has ended. As I mentioned, there are so many reactions in this chapter. So I covered hydrogen and oxygen nucleophiles. But I think what I'm going to do for you all is I'm not going to hold another review session. What I'll do is I'll record my own review session on my own time and then post that for you, showing the other nucleophilic attacks that we can have, because we went over these 2 and I want to go over those 3 more. Although the carbon nucleophiles are with Grignard reagents, so you all have already seen that in chapter 10. So Grignard you're familiar with. The ones you're not familiar with are sulfur nucleophiles and nitrogen nucleophiles. So I'll try to make a video sometime between Monday and Tuesday and I'll try to post it on Blackboard so you all can see the other reactions of carbonyl nucleophiles. But for now, are there any questions, students? Anything you want me to explain? Anything else you want me to do? It's a very long chapter, I know, but y'all are doing great. Y'all are doing excellent. And I know that you have the capacity to do very well on this quiz. So like I said, we went over these two, and I'll go over these last three in a separate video recording. You're welcome, guys. Okay, so there's no more questions. Then I'm going to stop the recording, and I'm going to wish you all a very nice Sunday evening, and I'll see you all tomorrow in lecture. Have a nice day. So that was the mechanism for question number 3. In question number 4, I will answer it in the continuation of this video. So make sure to go ahead and click on the next O nucleophile video.